So last time we spoke, we came up with these projectile motion equations. Now you can see there's all sorts of things here, you know, launch angles and x coordinates and y coordinates and maximum heights and how far our projectile travels. So it's going to be impossible for me to do every single projectile motion question where you find every single thing. So in this video, I'm just going to talk about some like basic principles and some ideas that you'll be able to use in projectile motion questions. Okay, so first things first, if we were to launch one of these again, what we get is this thing here, but we get a path, right? We get like this path here. If we had the Cartesian equation of this path, so if we got rid of the t and just had the path of this in terms of x and y, we might find that really useful. So you do this the same way that you would find any other Cartesian equation of a vector equation. Let's choose a different color here. This bit here describes the x coordinate of our dot at any given time. So x equals the magnitude of our velocity cos launch angle t. That's it there. And this piece here describes our y coordinate at any given time. So we have y equals negative g over 2 t squared plus the magnitude of our launch angle, and t. Okay. And now we need to like get that equation into that equation. So this equation can be rewritten as x over the magnitude of v cos theta t. And then I'm going to sub that into here for t here and for t here. I'll be right back. All right, so I substituted this for t here and this here. And then we can tidy this mess up a little bit, because we can say y equals negative g on 2 and then x squared, so that can go there, the magnitude of velocity squared, and then cos theta squared on the bottom. But instead of putting cos theta on the bottom, we can put it on the top as sec squared theta. All right, so we have negative gx squared sec squared theta over 2 the velocity of the launch squared plus, what do we have here? Velocity sine theta times x. Oh, there's a velocity, so they're going to cancel each other out, so we don't have to worry about them. And then we have sine theta times x over cos theta. Sine theta over cos theta is tan theta. So this whole piece here is just tan theta x. Okay, looks complicated here. Remember, g is a number, it's 9.8. Theta, that's a launch angle, which potentially we have or are trying to find. This is a velocity of our launch, which is probably a number. And tan theta, if we know our angle, then this is also a number. So this is an equation where this, it's all numbers except for y and x. This is the Cartesian equation of a projectile. Write it down. You might find it useful. You should also be able to just derive it as you go. So what if we wanted to calculate flight time? What if we were watching our object here, traveling through the sky, and finding out how long until it hits the ground? Well, think about our object. It hits the ground when its displacement vector, that orange vector along here, when its j coordinate is equal to 0. So the simple answer to that is let j coordinate equal 0. So let all of that equal 0 and solve it for t. Now remember, you know what gravity is, you know what the velocity and launch angle are, you're trying to find out when does it hit. Okay, so that's flight time, let the j coordinate equal 0, solve it. Now what if you wanted to find flight distance? My projectile's got about 190 meters here. If I know flight time, and I just found flight time by letting the j coordinate equal 0, then I should be able to find flight distance by subbing t of flight time into the I coordinate. Right. So if I find out that the flight time was 6 seconds, I can sub 6 seconds in here, and that'll tell me how far this thing has traveled. Okay, that's flight time, that's flight distance. I should say, it's not the only way to find flight distance, right? Because just before I showed you how to find a Cartesian equation. If you know the Cartesian equation, you can just find out when the Cartesian equation is equal to 0, and that will give you your x-coordinate of your flight distance. So what if you wanted to find the maximum height? So let's go back to time equals 0, and we're flying through the air. We don't need to see the displacement function. Stop. Let's look at the velocity. Let's look at the velocity components. Let's just scrub backwards a little bit. We're reaching our maximum height when the j component of the velocity is equal to 0. So maximum height at velocity j component equals 0. So if we want to know when our projectile is at its maximum height, take your velocity function and let this portion of it equal 0 and solve it for t. Now, of course, maybe you don't want the maximum height. Or sorry, maybe you don't want the time when the maximum height is happening. So what we've just found is the maximum height time. Maybe instead you want, well, how far across has it gone? Mine's gone about 90 meters at its maximum height. Once I've found this, obviously, I can then take that time and sub it into our displacement function, and that'll tell us how far across it's gone. Of course, you can do this with the Cartesian equation as well, but if you were asked at what time is it at its maximum height, the Cartesian equation might not help you as much. Now, an interesting question might be landing angle. So, if we launch, we know our launch angle right there, right? Our launch angle is, at the moment, 42 degrees. If we launch that, and it flies through the sky, and then it's coming down to land, doom. Okay, where it lands, the angle that it makes with the ground is actually going to be equal to its launch angle, right? If we were to turn on a trace, that makes a lot of sense. The angle that it's launching at is equal to the angle that it's landing at, because its flight path is symmetrical, at least in our idealized world, without air resistance. So there's a big but here, equal to launch if launched from ground level, right? If we're not launching from ground level, we've got to work a bit differently. So if I launch from here, I've just decreased velocity a bit so we don't have to watch this thing fly through the sky for the next 10 hours. You can see that the launch angle is different to the landing angle, right? This launch angle is 42 degrees, but this landing angle is much, much steeper. And if we were to launch from even higher, the landing angle would be much, much steeper again. So how do we find that? Well, look at my projectile right there, right? So I've launched my projectile. These blue components are my velocity components. My velocity in the I direction and my velocity in the J direction. And you can see that as we launch, as we land, boom, we get this angle here. All right, and that angle there, if we kind of stretch up this way a little bit, we do that, that is equivalent to our landing angle. So this angle is equal to that angle there. So if I can find that angle, I'm in business. Now, what is that angle? Well, a little bit of trigonometry shows you that it's equal to tan theta, where this bit's theta now. Tan theta is equal to opposite which is the j component of our velocity, divided by adjacent, which is the I component of our velocity. So for uneven ground, tan theta is equal to velocity in the j component at the time of landing. So you still have to find the time of landing over the velocity in the I component at the time of landing, if launched from anywhere that isn't ground level. Okay, let's get rid of that. So a couple of non-standard questions that teachers like to throw at you, because we've been looking at all of these projectiles going whee across the page in this direction. So I want to throw 3 non-standard questions at you. And all 3 of these non-standard questions have the same sort of thing that I'm changing here. It's the launch angle. So we've got our launch here, there's our launch there. I'm going to change my initial launch to something that looks a bit more like that. Boop. Okay, that is a bullet from a gun. Someone is shooting a projectile straight. What does it look like? It looks like that. Whee! It's still projectile motion, right? You can see it's like curving down like that. Do all of these formulas still work? Yes. What is our launch angle? Our launch angle is 0. So you don't have to change anything. You don't have to get all fancy with it. You just change your launch angle to 0. Okay, so first one, the bullet. The second one is a object falling off a roof. Okay, so you've got like a house, and your object rolls off the roof and falls down. Like it builds up speed, rolls off the roof, falls down. Its launch angle is negative. So something like that. Okay, my app's a little bit broken. I've got a launch angle here of negative 25 degrees. And again, we can see it just does what projectile motion does. So we roll off the roof, our launch angle is downwards. Does it have to be like launching off a roof? No. You could be like an archer at the top of like a castle turret firing down towards the enemy, I guess. And for my last one, a classic of the genre, we're going to really move our initial position by a long way. We're going to move it over to here. It doesn't matter how high or low it is, but we're going to move it over to there. And then we're going to shift our launch angle. Our launch angle somewhere between 90 and 180. Now, again, this is a classic because what we can do here is have someone firing cannonballs in this direction and someone firing cannonballs in this direction, and then like maybe they're going to like smash into each other, and we figure out like what angle is required to make them smash into each other, what launch velocity is required to smash into each other, at what time will they smash into each other, whatever it is. But the first thing we need to do if we're confronted by 2 projectiles going in opposite directions is deal with this one. And the easiest way to deal with it is just to give it an angle between 90 and 180 degrees. Can I imagine we combine this archer with the idea of this? So a projectile coming from here and this one here, castle turret, and we like push that angle even lower like that. I haven't even created my app to do it, but could I imagine something like that? Like, ooh, yes, I can. But my third option here is we're launching somewhere between 90 and 180 degrees. So they are my 3 non-standard questions. Launch angle of 0, launch angle less than 0, and a launch angle between 90 and 180. I guess maybe we can amend that to a launch angle between 90 and 270, but we're really starting to mix up our non-standard questions there. All right, that's all I've got for this one. I know I've covered a lot of ground here and I haven't done a single worked example. I feel bad for that, but if you're the kind of student that's doing projectile motions and really trying to do well here, projectile motion is not a simple familiar question. It's a complex unfamiliar question, so you know that teachers are going to push this a long way. So if you want to do well in these sorts of questions, what you need to do now is take everything we've spoken about, grab as many questions as you can and try to work through them slowly and ask yourself, okay, what are they asking me for here? How can I find that? How does that relate to displacement? How does that relate to velocity? How does that relate to acceleration? Will the Cartesian equation of the path help me? And you can do it. There's also almost always more than one way to solve these. So if you're doing it a different way to like a work solution or something, don't panic, just see if you can get to the right answer. All right, projectile motion.